30 short proofs that the Earth is flat. Follow if you're curious why people believe in it.
This is a video that someone on TikTok sent me. So it looks rather funny. Let's have a look. Let's get into it.
Physics and logic on a level supreme. It's a curved reality, splitting flurf dreams.
Look at how sun rays break through the clouds. See the angles? They spread out in different directions. That suggests the sun is not as far from the clouds as we're told. If the sun were 93 million miles away, the rays would appear parallel.
Right, I've heard this many times from flat earthers. They think that the sun is really local, and because you see the like if the sun is blocked by clouds and stuff, they see the sun rays, and they think they diverge out. It's actually the same concept if you would look at train tracks and look down a straight set of train tracks. It looks like as you go down, they converge to a point. They actually don't. It's called perspective. Now, a lot of times flat earthers don't understand perspective, and they try to claim perspective accounts for refraction, atmospheric refraction, and bottom-up obstructions. But that's not the case. And this is down to the fact that flat earthers don't know what perspective is. This is perspective, which they will deny. And then when you look at something like a ship disappearing over the curvature of the Earth, or the fact that we can see something a bit too, if you have a bit of atmospheric refraction, or you can maybe see something, see a bit more because of the atmosphere, because of the light rays bending down into our eyes a bit, then they'll just deny all that too and think that it's down to perspective. Perspective doesn't make things disappear bottom up. I'll show you a few examples of light rays, crepuscular rays is what this is, the sun's rays, looking from above. And I'll show you an example of what I can show you. I can simulate the same sort of thing with just using a fence that has a bunch of parallel bars in it, or like, kind of flat metal stuff like that, and with the sun, and you'll see the same exact concept. So you can see these fence panels look like they are converging at one point from the sun on the other side of this fence. But when we look at it straight from above, they're actually all parallel to each other. This is the same concept as you'll see with the crepuscular rays. So this crepuscular rays seen from above, from like a plane or like the ISS, and you see that they are all parallel to each other and not converging to a point.
Airplanes always fly straight. On a globe, they'd have to constantly tilt downward, otherwise they'd drift into space.
So this is the misunderstanding that flat earthers just don't understand, is how planes are actually able to fly. Where they use something like, you have different forces acting upon a plane. Obviously, you have the lift under the wings from the speed going forward. So you have thrust that's going to obviously push the plane, propel it forward. You have lift generated by the wings, which will help it to lift to gain a certain altitude. But you need a certain amount of air pressure and air to generate that kind of lift. You get to a point, and this is where planes have a service ceiling. If you get too high up, then there's not enough atmospheric pressure or air to generate the lift under the wings, and you get a stall situation, which the plane will stall and it will drop back down, or you just won't really generate any more lift. So like say a commercial airplane, like the service ceiling could be something like 40,000 feet max. They tend to cruise at maybe, in more like the 36,000 feet. And that's just down to the fact that the jet engines aren't able to bring in enough air to generate enough thrust, and the wings aren't able to generate enough lift up. So like I said, you have thrust pushing forward, you have lift under the wings, you have actually gravity, which is still pushing down on it, but the lift is overcoming that gravity. Now, if you slow down too much, or you throttle down, then the plane will start to descend. How planes tend to how to ascend and descend is what they do is they have an attack angle, which is usually about, let's say, 3% nose up, 3 degrees, sorry, and they throttle up to gain altitude, and they throttle down and they'll lose altitude. And that's where you can see how planes can land, and they land with the noses up still. And this is down to the fact is that they've just as they throttle down, they go down, and then sometimes what you'll hear is if you're on a plane, it's just about ready to touch down. They're throttled up a little bit. What that does is just generates a little bit of lift as the plane is still going down. It just kind of slows the descent and allows the plane to touch down a bit more softly. So you hear them kind of come down, then you hear them kind of throttle up as they go like that, woo, and then they'll land nice and gentle. And that's just, so that's kind of how planes are able to, ascend and descend, is simply just by increasing and decreasing the thrust from the engines. I'll put up a little graphic that shows that I think there's 4 main forces are acting upon, because you also have drag. So you have thrust, lift, gravitational pulling down, and you also have drag, which is then obviously pushing against the front of the plane that slows it down, and you actually generate drag. I think there's usually a 5th one, but those 4 are the main ones. Also, meaning modern aircraft now, especially commercial aircraft, has something called INS system, which is inertial navigation system, and it allows the attitude indicator, because it's all done in electronics. It uses some accelerometers, which are trying to maintain this the gravitational pull going straight down. Then it has some gyros, and then what happens is it has a couple of motors, and as the gravitometers feel that they're too long, if it's not getting the thing down, it'll actually move those a little bit, and so it maintains the as it's going over the curvature of the Earth, this system actually automatically adjusts itself to compensate for the downward vector. And this is why if you see planes when they're seeing a holding pattern, maybe waiting to land, they will actually go long straight, turn quickly, and go long straight. And why they don't just sit and do this is because what it'll do is if they kept doing this, then you'd have, let's say, the bank. Then what happens is the INS system will start to feel the outward vector of the force, so the tangential force going around, and it will start to change the false horizon, or the attitude indicator, to simply make it look like it goes level again, because it'll compensate for that downward vector, and the accelerometers and stuff will be feeling that, and the system will assume that is the downward vector of the gravitational pull of the Earth, and it will actually compensate the whole system for that. And so that's why they do straight turns, a quick turn, which the system is fine for that. It'll allow everything, all the instruments work fine, and then they go straight. And so what does that allows the system to feel the gravitational pull again, go straight down, so they'll have a level flight, and then they'll flip around again, and then go straight down, and they'll just do a holding pattern like that. But they have to have a long time going straight, flip around, and go straight again. And older planes, we have something like pendulous vanes, in which they had a system that had air going through it. And if the air hole is all open on one side, it would actually move the pendulous vane to make it go back until both holes are blocked. If you have maybe 2 holes on each side, and it would make it until it blocked. Then it knew that it was calibrated that was the downward vector, that it was level flight, and that was a gravitational pull of the Earth. And then you can bank fast each way, but if you were to but the system can compensate faster than the plane can fly over the curvature of the Earth to compensate and keep the attitude indicator to be flying straight. These are 2 of the systems. There's actually other systems that were earlier than that were invented, especially when planes were able to do a big enough distance that the curvature of the Earth and stuff like that was a problem. Before that, what they'd have to do is that every so often, the pilot would have to look and know that they were flying fairly level, and then they would have to cage the attitude indicator, the gyro, and adjust it so that it was giving a true reading again. If they're doing just a constant flight at a certain pace, and they knew that everything else was indicating they're on a level flight, and the attitude indicator would be off, they cage the gyro, adjust it, put it back to where it should be, and then continue on. And they knew every maybe 8, 9, 10 minutes, you'd have to cage it, do it again, so that it was accurate for when they had to do different maneuvers. So, yeah, that's just a quick rundown from what I've learned from how airplane and gyroscopes and attitude indicators work in planes. The 4 main forces that are acting on plane and flight is thrust, lift, drag, and gravity. Here's an example of INS system, which helps a plane to fly level over the curvature of the Earth as it's going on its journey.
Water always levels itself. If we were on a sphere, oceans would be in constant chaos, but they're calm.
What? Oceans are calm? Fuck, has he never seen any kind of ships on the ocean ever? I'll put a video up here of some large cargo ships on the ocean. You tell me how calm they really are. Water can be contained and is subject to the forces acting upon it. So in this case here, we have the gravitational pull of the Earth acting on all matter. Oceans have a lot of matter. Oceans are very big, lots and lots of water, and so they are held to the surface of the Earth. But they are also subject to different weather patterns and stuff, because you have other forces that could be acting on the water as well as a gravitational pull. So you tell me here, I'll put up a video now of the oceans. You tell me that they're calm. Go on.
The relentless power of nature puts these ships to the test as the sea unleashes its fury. Here are 10 ships caught in massive storms. Number 10, a warship smashes into a gigantic wave near Antarctica. Number 9, a Russian oil tanker gets hit by a monster wave, which almost capsizes the ship.
Now, I'm not going to show you all 10 there, but you get the idea. Do those oceans look calm to you? Not a fucking chance.
There's a huge difference in temperature between the equator and the poles. On a flat Earth, the sun circles above the equator, which would explain the heat. If the sun were really that far away, the temperature difference wouldn't be so extreme.
No, because like the sun is like really big, 93 million miles away, but there's a lot of energy that is being sent through space that hits the Earth, and then it heats up our atmosphere, and this is what causes the temperature changes. Is we have a lot, when we're facing more towards the sun and you get a lot more of that direct energy hitting us, it helps heat things up more. And then when we're on because of the tilt, if we're in the wintertime, then a lot of heat, that energy is being reflected off the atmosphere. We're not getting nearly as much directly hitting us. It's not affecting the atmosphere as much and not heating it up as much. But on the bottom, like the southern hemisphere, because we're in the northern hemisphere here, then they're getting more direct energy and more that's getting through the atmosphere, and it's heating up the atmosphere. That's how that works. Flat Earthers, can you explain to me, how does the sun float above the flat plane? What's holding it up there? What causes it to rotate? What causes it to spin around? And what causes it to move up and down in the for the tropics? Because no flat earthers ever explained this to anybody. Also, why is it that when we go higher up, because if the sun's so local and it heats up the whole Earth, why is it when we go up it gets colder and not warmer? Because you should go like super hot. Like planes should be like nearly melting, especially when the sun's just above them flying, because that does happen, right? So why don't planes just up and melt? Like that, what's causing that? That's why are you not getting like hundreds, if not thousands, degrees of heat if the sun's so local and it's a source of our heat on a flat plane, and and the sun is so close. That doesn't work at all. In fact, the fact that the sun provides the heat to us and that also it proves that the Earth is a globe. Also, in fact, why can't I see right now? It's dark where I am. Why can't I see the sun? Because the sun is, I'm still in the summertime in the northern hemisphere. The sun actually see it quite close because flat earthers claim it's 3,000 miles above the Earth, and if it's like a ball or something like that, why is it that I can't see? Why is it not lighting up the sky? Because I should be able to see it. 3,000 miles actually isn't that far, isn't that high up. I can see stars past Polaris on the other side. I can see Polaris above, and I can see stars further. And if they're in your magical dome, then those are further than 3,000 miles away. but I can see little tiny stars, but I can't see the sun and the sun's light. That doesn't work. I've modeled this out, and it lights up the whole entire Earth at all times. So, yeah, your local sun heating things up and like that doesn't work at all. It fails at so many different levels. Nice try, though.
The temperatures on other planets also seem strange. For example, Mercury is colder than Venus, even though it's closer to the sun.
Well, that's easy to explain. Mercury doesn't have an atmosphere. All right, the atmosphere is burnt off, was stripped away by the sun billions of years ago. Venus, on the other hand, Venus is far enough away that it actually has a very thick atmosphere, and a lot of thick clouds, thick atmosphere, and it holds a lot of heat in. So as all that energy is hitting that planet, it's keeping it in. It's just a massive greenhouse effect. Venus is just a massive, huge greenhouse effect, and I think also atmosphere has got a lot of sulfur and other things in it, which is just generates a lot of heat. So Mercury is cooler because it has nothing to hold the heat in, and so that heat just that sun's energy is hitting, but it doesn't have an atmosphere to really be warming it up and be holding it in. But Venus has a very thick atmosphere, a lot of cloud cover that holds all that heat in, and so the temperature is much higher, as because it can just hold that heat, get more and more energy coming in, and it's just all the energy is being held in and is acting on a thick atmosphere. So there you go. Not a problem, easily explained.
The horizon looks flat at any altitude, no fisheye lens. You can see this from high altitude balloons.
No, see, the horizon doesn't look flat at any altitude. And in fact, if you go to the beach right now, and you can see things disappearing over the curvature of the Earth. The fact that we have a horizon, like a sharp horizon, that falsifies the flat Earth. If the Earth was flat, all you'd see this keep ramping up. You go. Things rather go smaller, without ever disappearing bottom up until you couldn't resolve them anymore. Or things would just keep going off and off. All you see is just the land or the ocean and stuff would just keep going off, and then eventually this kind of would get harder and harder to resolve. It get fuzzier and fuzzier because of all the atmosphere between you. And you'd go hundreds, if not thousands of miles out, and you'd still be able to make some stuff out, but it'd just be really fuzzy. But because we have a sharp horizon and you see things kind of disappear bottom up and go over top, that falsifies the flat Earth. There's many different things, like Kip Bogard, who sent a rocket up that had a rectilinear lens, so it wasn't fisheye, showed the curvature of the Earth very clearly. You can look at things like different rocket launches. You can look at the Himari 8/Himari 9 now. It shows curvature of the Earth. The EPIC satellite, which is in geostationary orbit, that shows the full disk of the Earth. You can look at stuff like NOAA's satellites that goes east, goes west. Satellites, they show different portions of their geostationary orbit. They show the curvature of the Earth. And there's also a company called Verta Space Industries, and they do this thing where they have these probes that go up and they grow a certain crystal for this special medicine. And they actually have a camera on there that's not a fisheye lens, because you have a straight line there, a straight line there, a straight line there, and it looks out, but you can see the curvature of the Earth. I'll put a little video up there showing that. But yeah, there's loads of stuff that's shown there, as well as that we've had weather balloons have been sent up to high altitude that don't have any fisheye lenses, rectilinear lenses. I think a fella named Mr. Sensible from the UK, he sent a high altitude balloon up that he had, and he actually had a piece of string drawn from side to side in front of the camera, so that you can see that it wasn't a fisheye lens. They were perfectly flat, and you can see how they've done this. Look at on his YouTube channel, and he showed the curvature of the Earth between that, and he had the piece of string to show that there was no distortion to the camera whatsoever. So this has been done many, countless times, all showing the curvature of the Earth. Flat earthers just like to lie. Here's a bit of a clip from the company Verta Space Industries. This is a probe coming in, and as you can see here, it's not a fisheye lens, as all the lines on the probe are straight, but yet you can see the curvature of the Earth very clearly here. Oh, look, there's also the sun way off in the distance, obviously not local. Holy crap, look at that, eh? Killed 2 birds with 1 stone right there. Holy. So yeah, we're just gonna have a little look here. But as you can see here, it's this is just on re-entry. They have done this several times. This is kind of what they do for a. They grow these crystals in this probe that goes around the Earth, and then they can they show this little videos as they come back. So it's definitely curvature of the Earth, clearly seen in there. Not a problem. This falsifies the narrative flat earthers like try to push, and yeah, it's definitely not a fisheye lens, or else all those lines would be distorted, and you can see the brow distortion. Those lines would be all bent up and either bending one way or the other, but they're not. You can see how they're completely straight. So this is factual evidence and video.
Ships can see lighthouses from very far away. On a curved Earth, this shouldn't be possible.
Why shouldn't it be possible? Lighthouses are usually very tall, and sometimes they've been built on like high cliffs or like high bits of land, like maybe on an island that kind of rises up. And you do see these over like the ocean because they're tall to see over the curvature of the Earth. And that's why lighthouses are the way they are. Why they're either built up on a higher bit of land, maybe on a cliff edge, or why they're in like a taller bit of land out in the middle of the ocean. And also they're built to be a high structure. If the Earth was flat, then lighthouses could only just be a massive light that's just be on top of a regular type of house, or could just be a light that's just sitting on the land itself, and this could just be sitting on the water. Like, you wouldn't need to have these really, really tall structures. But I'll show you a little bit here of how lighthouses work and why they have to be the height they are and how they work on the globe. But yeah, the fact of how lighthouses are built makes absolutely 0 sense if the Earth was flat. So the lighthouses themselves and the fact that they have to be so tall is evidence for the curvature of the Earth, because the necessity of them being the height they are is due to the curvature of the Earth and the fact that Earth is a sphere. So here you see why lighthouses with their height of a boat so far away, you can't see the light from the lighthouse because of the curvature of the Earth. And then when you get to within a certain distance of the land, then they'll be able to see the lighthouse. So you can either know where the land is or where like maybe an entrance is into a bay or something like that. Also, as ships get closer to where a lighthouse is, they won't be able to see the lighthouse itself, but they can see where the light starts to show over the horizon, and then they'll eventually see it as you get closer, and they can see over the curvature of the Earth.
Some flight paths don't make sense on a globe, but they look much more logical on a flat Earth map, like Sydney to Johannesburg.
Alright, this is often cited by flat earthers, and I think this just comes down to the fact they don't understand the basics of like how aircraft company or like a flight company would work. Sometimes you have connecting flights because there is more traffic going to, like, so from this one here, maybe there's a flight that goes from Sydney to Dubai, and then from Dubai maybe to Johannesburg. But on that particular flight, there is direct flights from Sydney to Johannesburg. And wouldn't you know it, it doesn't actually work on a flat Earth, but it does work perfectly on a globe. And I'll show you. I'll show you a flight that is happening soon here, and I'll show you the path they take. And this that would not make no sense on a flat Earth whatsoever. In fact, the distance would be far beyond what any commercial aircraft could actually make in non-stop flight. But this flight actually happens quite regularly. So here shows the flight that goes from Sydney, Australia to Johannesburg non-stop. Takes 14 hours, and it shows the distance there. And just this month alone, it happens nearly every single day of the week for the whole month. I've plotted this out on a globe, starting in Johannesburg, South Africa. We're going to do a direct flight, the route they take, straight to Sydney, Australia. And as you can see, this flight, this is the path that you take. You can look at this on Flight Radar 24 if you want. And this 100% is the route that it'll take. plus or minus depending on weather conditions, but this is the route they take, and this is proven.
Especially when crossing the Pacific, wouldn't it be easier to fly straight across?
It depends on what the destination is. There are flights that go from Sydney to Los Angeles, and then which they do go up that way. And there are some flights that go from Sydney to maybe to Los Angeles to New York. All depends on the route. There's also flights that go from Sydney to South America, like Santiago to Sydney, which happens several times a week. So yeah, it does. Well, it would make sense depending on where they're going, what the destination is. But some of those routes do happen all the time. I mean, you can go from New York to somewhere in Europe, or you can go from New York to somewhere in Africa. Easily not a problem. So yeah, all depends. All about economics, because any kind of a flight company, they want to make the most amount of money using the least amount of fuel with the most direct routes. And you want to use routes that are popular, that ones that make sense and that they're going to have, it's going to be financially viable. Sometimes flyers just seem to struggle with this.
And look at how flights avoid Antarctica. Strange, right? It looks like they're hiding something, but these routes make sense on a flat map.
A lot of times it's not financially viable to go across Antarctica. Like I said, the Santiago, Chile to Sydney, Australia, or even to Auckland, which is in New Zealand, which is fairly close. They go down and they go close to Antarctica, and then they come up. But it's actually a straight route if you were to plot it looking at a three-dimensional globe. Now there is reasons why they don't go across Antarctica, and it is down to the fact that there has to be certain ratings for planes, that they have to be within a somewhere to land if there have to be emergency, and and how far they can go on one engine. And this is just to do with safety regulations, that if they ever happen to have an engine failure or failure of some kind, that they could be able to get to somewhere safe to land, and maybe get maintenance or get other or switch planes, switch people, and be able to get there on one engine. And the planes, modern planes, are getting where they can go further and further on one engine and more efficient. But going across Antarctica, which is a really harsh land, there is nothing within a range that you could land a commercial jet safely and be able to fly, or to fly if they happen to be over the middle of Antarctica, to fly somewhere safely to on one engine. There is some flights that have done that. I believe that in 2019 or 2020, Qantas had to repatriate some people from South America, and they decided that the quickest way, or how to get them across, because they had to get to they had to get to Darwin, Australia, which is actually more kind of on the north west side, and they actually flew over top of Antarctica, and they it wasn't directly over top of the South Pole, but just off to one side, and came over and landed in Darwin, Australia. You can look this up. I think it holds one of the longest records for longest single commercial flight. It was just a few people, so they had very little weight, and so they were able to do an extended distance without having so as many people on, and it was just like a rescue mission sort of thing. But they did notice in this here, they showed the flight from Santiago, Chile to Brisbane, Australia, and I'll show you the flight, how that works on the globe, and you'll see why it's not they avoid Antarctica, but there's absolutely no need to go across Antarctica to make that flight. Here's showing the flight going from Sydney, Australia to Santiago, and I'll show you the route they take. This is the route they take. So starting in Sydney, Australia, and go to Santiago, Chile, and so land there. And if you look up this on Flight Tracker 24, this is pretty much the exact route they take. As you can see, there's absolutely no need to go over Antarctica. In fact, it would make it longer needlessly, and the flight companies want to try and make the most efficient route. So there you go. From Sydney to Australia, from Sydney to Santiago, this is the most direct flight and it works perfectly on a globe, and this is definitely the route that they take. It can be verified if you like.
We see full moons in the day, even when Earth is supposedly between the sun and moon. That's not how shadows work.
You can see full moons during the day on a globe. Makes perfect sense. It's not as a common occurrence as you might think. And it tends to happen just after sunrise or just before sunset, and you'll see a full moon. And that could be explained on a globe. And I think what flat earthers don't realize is that the moon's orbit isn't perfectly in line within the Earth. It's actually slightly tilted, so it at times either the moon is above or just below, or depending on what time of year it is, from the plane or from the Earth, so then you can see it perfectly fine. There's only 2 times during the year in which they are actually line up, and that's when you'll get, it's the seasons which you'll usually get your eclipses, either your solar or your lunar eclipse. And that's because as the moon's orbit is kind of tilted, there's certain times in which then at that middle point there, it will line up, and that's what I say around April time, you'll see either a lunar or a solar eclipse. And then I think it's in September time, then you'll see either the same thing, and it's those 2 points of the year. Other than that, the moon's actually slightly above the plane or slightly below the plane of the Earth, and that's where you see the full moon. I'll show you the example I did by using my globe, a light source, and a tennis ball, and you can see how you can easily see the full moon from daylight or from night side, either side, and it works perfectly using the globe model. So here you go. Here's the globe here. I got a light source there representing the moon and the sun or something, and I got a ball in my hand representing what the moon looked like. So here I'm sitting on my camera on the light, and then the dark side going back and forth, representing either just after sunrise or just before sunset. And you can see how you can see the full moon lit up by the sun, and this makes perfect sense, and you can see how that works out. Remember, the moon is 250,000 miles away, and the sun is 93 million miles away. They're not really close, and this is something that flat earthers simply can't grasp.
Why is the sun so bright during the day? If other stars were even brighter and bigger, shouldn't the night sky be just as bright?
The sun is really bright during the day because it is technically our closest star. It's 93 million miles away. Now, in the astronomical sense, that's local. That is really close. It's 8 light minutes away from us. So when the light leaves the sun, it takes 8 minutes to hit the Earth. We also count that as 1 astronomical unit, 1 AU. Now, our closest other stars to us is just over 4 light years away. So you're looking at a vastly much further distance to our next local star, which is what our sun is. And so why don't they light up? Because our closest star being our sun is 8 light minutes. And the next closest one is just over, there's 2 of them. They're a binary star system, I think. And they are just technically a little bit over 4 light years away. So why don't the other stars light up the Earth at night? Because they're really fucking far away compared to what we have. This isn't a difficult thing to think. So all that, they're not very close, so they're not going to light it up. Why is it that a street light 5 miles away doesn't light your house, but yet the street light in front of your house seems to light the front of your house up? I don't know. Let's think of that for a second. As I said, the closest star to us other than our sun is Proxima Centauri, and is just over 4 light years away.
They say the planet spins at 1,000 miles per hour, plus the sun moves, plus the galaxies spin. That adds up to insane speeds. Yet we feel nothing. Wouldn't there be chaos?
Well, I know these big numbers are really difficult for flat earthers to understand, but let's just put it in simple. The Earth rotates 1 revolution per day. That works out to 0.00069 RPM. Okay, look at your hour hand on your clock. Can you see that moving? Now think about something. Now watch the hour hand, but think of it moving half of that speed. Is that fast? No, it's not. Or you can try something. You want to try the demonstration. Standing living room, look at a point. Then I want you to do a full revolution, turn around completely to look at the same point again. But take 24 hours to do that. Now tell me, is that fast? Now, they say, oh, the Earth going around. Okay, yes, we're talking maybe from point to point. You can say that is a really fast speed to make that distance. But we orbit the Earth, the sun, pardon me. The Earth orbits the sun one complete revolution in 365 days. Now, can you think how that takes a whole year to go around once? You can see the speeds are fast, but is it really? Then let's talk about the galaxy. For us to make one revolution around the galaxy, it takes just over 256 million years. Now you can say, oh, the speeds, but let's just think that one full revolution is 256 million years. Humans have not been on this planet for a full revolution of us to go around the galaxy in the arm of the Milky Way galaxy we are in. We have not been around long enough to experience a full revolution. So you can say, would we feel this? How would we feel any of these things when they do the full revolution, which they think all the speeds, but to do that, it takes that long to do one complete rotation of the Earth takes a full day, and for us to go around the sun once takes a full year. So I know these big numbers sound insane, but let's just put it into a bit more, logical ideals. So, and then we were evolved and born and are made to be on this planet. So all this stuff we don't feel. Our bodies are not meant to feel these kind of things. One is constant speed. We don't feel constant speed. We feel acceleration and deceleration, which you don't experience. And then also our bodies are not designed to feel the the motion when it takes that long. We are not designed, we don't have any kind of organs to feel stuff like that. So, and then also the Earth has gravity, a gravitational force, which is greater than the forces applied for even the Earth to do one revolution for a day. So, yeah, it's not that astronomical to think of when you put it into a bit more logical sense. But, flat earthers like to try to make these big numbers because they sound really scary. But they really aren't.
Planes shouldn't fly the way they do. They'd either reach too fast or miss their destinations.
Well, the funny thing is, planes fly through the atmosphere of the Earth. And the atmosphere of the Earth rotates the same as the Earth does, right? It's called conservation of motion, and you actually, because of the gravitational pull of the Earth, you're getting a little bit of friction that's pulling all the atmosphere down towards the Earth, and then obviously the revolution is moving with it. But saying that, planes do take a little bit longer flying one way, going east to west compared to the other way. And it's easy to show you this. I'll show you my Santiago to Sydney flight. Let's check it out one more time, but let's look at the flight times. One going from Santiago to Chile to Sydney, and one going from Sydney to Santiago. Let's look at the flight times and see if they're the same. It's the exact same route, same destinations, but the flight times is slightly different. So look at this again. Why is it going from Sydney to Santiago takes 12 hours and 50 minutes, but to go from Santiago to Chile takes 14 hours and 45 minutes?
Weather doesn't seem affected by gravity. If Earth spun that fast, weather would be completely unstable.
The you say weather isn't affected by gravity? I mean, have you never seen snow falling from the sky or rain falling? That's due to gravity. Yeah. And yeah, actually, weather patterns kind of prove the or actually can show evidence to the shape of the Earth. You ever hear something called the Coriolis effect? Well, in the northern hemisphere, storm systems rotate counterclockwise. At the equator, stuff pretty much goes the same, and you go south of the equator, in the southern hemisphere, star systems rotate clockwise. You'll never see a hurricane cross the equator. Because of the rotation of the Earth, what happens, and you have the winds going very fast at the equator. As you go up, the winds are going a bit slower. So what happens is, because the winds are going faster, and then things go slower, it causes the wind patterns to go. These obviously come as they come up. They come from the equator and they'll work their way up. They're going faster. Then they're going faster. The winds go slower, so then causes a rotation like that. Now, if they go south, and the winds come south of there as it moves down there, the winds from the southern hemisphere are going faster than there. So as it comes down, the equator going faster, they're going slower, so it causes the opposite rotation. Now, I'll show you an example of this from a weather radar that I literally just took now. And you can see this if you look at the weather patterns or watch different hurricanes or tropical storms at different hemispheres, northern and southern hemisphere of the Earth. Let's have a look. Now, this is all down to the gravitational effects of the Earth. The fact is that gravity holds the atmosphere to the Earth, and then the rotation of the Earth. So we're going to kill two birds with one stone. So let's have a look. This is the weather radar I just done, so it's over the last maybe 24 hours. I didn't actually time it. But the southern hemisphere, as you see, the cloud patterns, they were going clockwise. Now you look at the northern hemisphere, look at the cloud patterns, they were rotating counterclockwise. And at the equator, you'll see that most stuff kind of goes pretty much the same and it veers one way or the other. So look again here, and you'll see that the weather patterns, northern hemisphere counterclockwise, southern hemisphere counterclockwise. This is down to the rotation of the Earth, and the gravitational pull of the Earth holds the atmosphere to the surface of the Earth, and that is what helps create the Coriolis effect. There you go.
Bullets shot straight up land only a few hundred meters away. With rotation, they should land far off, even kilometers away.
That's a really stupid and pointless example, because there's something called conservation of motion. Maybe flat earthers need to look this up a little bit. It's one of Isaac Newton's 4 basic laws. So if you were to have that gun in perfect 90 degrees and fire it straight up, then that bullet is leaving at the exact same velocity as the rotation of what that gun was at the point on the Earth. Let's just say the Earth is a globe. It's moving at wherever you are at the same speed. That bullet's going to go up and also maintain the conservation of motion of how fast that rifle or gun was moving at. Then how long is the flight time? 30 seconds. Then how it's going to come up and come down, and maybe only it's been in flight for 30 seconds, so it's going to lose maybe a tiny bit of speed, but it's still going to maintain most of that speed. It hasn't been in flight long enough. So that's a really stupid idea. Why would it be miles away? It hasn't lost that much speed, but a few hundred miles, a few hundred meters, as they said in this, that makes sense. So it's lost a little bit of speed, and now it's not going to land perfectly beside your feet or perfectly beside the gun or back inside the gun. It's a few hundred meters away because it's lost a little bit of speed. Obviously, we're not thinking of any kind of atmospheric conditions like crosswinds or anything like that. So, that's makes sense in the globe, and actually kind of falsifies flat Earth that they claim is flat and non-rotating. Thanks.
With that kind of spinning, water should fly off into space. Just watch how water behaves on a spinning tennis ball.
And once again, as I said before, the Earth rotates 1 revolution in 24 hours. That equals out to being 0.000069 RPM. That's not very fast. So now take your wet tennis ball and put it on, I see an example, put it on a mount for a telescope that is meant to help track the stars and stuff like that, like an equatorial mount. Turn that thing on and see how fast that moves. This is the mount that's designed to keep up to the rotation of the Earth, to watch celestial objects in the sky. Put it on there and then show me how much water comes off as that thing spins. Now remember, that ball is going to do 1 revolution in 24 hours. And you think the water is going to fall off that? No. Not going to happen. It'll probably evaporate before it flies off there. The whole tennis ball thing they showed there, that's like something rotating up probably faster than the speed of light in, if you think in, to scale it up to the size of the Earth.
Imagine we're in a vacuum, like they say. Look what vacuum does to sealed tanks. If Earth were in space, wouldn't it collapse too?
We have a pressure gradient, so yeah, it's not like high pressure next to a vacuum. It's and there's no perfect vacuum anyway. Space isn't a perfect vacuum. It's less pressure, and then you want to go towards Earth. It's a tiny bit more pressure next to a tiny bit more pressure next to a tiny bit more, and the closer you get to the Earth, a tiny bit more it ramps up on a scale. So yeah. As for the examples of showing those tanks, what they're actually doing there, that isn't the vacuum that's causing it to crush. It's all the pressure on the outside pressing in, and then when you move all that pressure on the inside, so what happens now, you have a massive pressure difference. So you've taken all the pressure that's on the inside that before was probably equal to the pressure on the outside, and you've removed it all, and it's all the pressure on the outside pushing in, because you've caused a massive pressure difference between the outside and the inside. And if you think of something like 14.7 psi, which is 14.7 pounds per square inch on that big tank, that's a lot of pressure pushing on the outside, pushing in. But we don't have that. We have a gradient in which as you go up, it's slightly less, next to slightly less, next to slightly less, next to slightly less. Now you can actually prove this. Most modern smartphones have an instrument inside which can measure different pressures. So download an app, go inside your house, and start at the ground floor, and then walk upstairs and watch your pressure drop. There you go. You have high pressure next to low pressure, and there's no physical barrier between, because imagine your house probably has no doors or any kind of sealed things between the ground floor and the next floor up, right? Everything kind of move around. So yeah, you can do it in your room. Put your phone on the floor, look at the pressure, then stand up and hold it at the ceiling and watch the pressure drop. No physical barrier, and yet you have lower pressure next to higher pressure. There you go.
Lasers shot over long distances stay level, they don't curve. Terrain may affect the result, but not Earth's curvature.
Now, flat earthers love to try to bring up this whole laser thing and all that. Now, the only thing is with lasers, they are subject to the refractive index of the atmosphere. And if you have very cool air near the bottom, like where they're doing it, and then it goes warmer up, then you actually will bend the light path. You will actually bend it down a bit. As well as also lasers are like any other light source, they will diverge. Now, lasers don't diverge as much as, say, a flashlight, but they still are subject, and they will still diverge from the source. So as you go farther out, the laser light actually diverges from itself and gets wider, which is sometimes why, if you look at some of these, like the one I've seen over the frozen lake, it wasn't a pinpoint. He actually had, when you showed it, he had to move around. He could see it. You could see sometimes it goes like dimmer, it goes brighter, it goes dimmer, and he had like a big, huge dot, and that's because that's just diverging away. I've done a very similar test with a laser I have, and you can see just like inside my house, the laser beam was like a pinpoint, but when I shot it down to like the end of the road on a wall, you can see it was much bigger, and that's just simply, like I said, this divergence. So flat earthers like to bring out these laser tests, but they're actually not a very good test for testing this because they're not accounting for the atmospheric refraction index, as well as then also not accounting for the divergence of the laser beam.
And if I set the zoom factor to 1, which means this is the actual size, you'll see things look very, very, very flat. The Earth, of course, it doesn't curve very much because it's so big. So over 6 miles, there's hardly any curve. It looks pretty much flat. We can zoom in to reveal the curve. We can see this is the spread of the laser beam. If I change the angle of the laser, you'll see the green lines in the middle, and there's 2 green lines, one on either side. This is showing the divergence of the laser. And as I said, it's been magnified because we're magnifying the curve. So we can see what's going on. So if I go back down to 1, it would actually look like that, which, it looks like a straight line, but it's actually diverging very, very slightly. Anyway, so this laser beam starts over here, and it goes in this direction, and the bottom of it spreads to here, and the top spreads to here. So if it's angled down a little bit, so it's down more like it was before, the top of the laser beam could be going way over the camera, but the bottom of the laser beam is just touching the camera, just managed to make it around the curve of the Earth. And you can see down here, you can just see that beam start to come in. So the divergence of the laser beam actually has quite a significant effect, and that it makes it very, very easy to see the beam kind of no matter what direction you're pointing it in, like up or down, because there's always going to be some light path which goes just over the curve of the Earth. Let me just get rid of this real quick. I'll just move it over here, and I'll move this into so you can see it a little bit better, and I'm going to zoom in a bit more. So here's the camera, and here's where the laser is. Both of them are 3 feet above the ground, and even though the laser beam is shining up like this, there's still a light path which goes from the laser to the camera, and you can actually see that by moving this around here until we get to the laser. So this yellow line here is a path that the laser takes. Now if we zoom down a little bit more, if it tilts down a little bit more, you'll see the laser will actually get brighter as the center of the beam goes closer and closer. Now, why is it refracting around? Well, it's because the water is cooler. And I've got this little graph here which shows this very, very slight cool water, then slightly warmer air, and then just moving. This is hardly anything. This is about 1/10 of a degree. It really, really does not take very much at all to get the actual results that we're looking for here. Now, of course, if the air was even warmer, then you get even more refraction, it becomes more visible. But if the air is just a little bit cooler than the water is warmer, then we don't see the laser. So very, very small variations can have quite a big effect. We can see the laser here. Move this over here. You can't see it. You can see it, you can't see it. And this, I'm just moving basically about 1/10 of a degree either way. So, and it's only in the bottom 10 feet or so, and it could be even less. I can focus down on the bottom like 1 or 2 feet, and just very, very small adjustments in the temperature. So because you don't actually know the temperature all the way along this path, all the way along this 6-mile path, it's actually quite difficult to figure out what's actually going on. And actually what you see in terms of what the refraction is a better indication of what the temperature is along that path than the actual measurements you would make, say, at the start and the end of that path.
Star positions haven't changed in hundreds of years. There's no visible parallax. Constellations stay the same.
That is actually completely wrong. We have many different star charts showing how different stars have changed, and some constellations have changed. And even, like, say, Polaris, you can see from even 50 years ago to now that its position has changed from just being over maybe, I think, 3/4 of a degree to now it's within 1/2 a degree of the being over the polar region of the Earth. And then if you even watch, though, it still does rotate around. It's not like perfectly in the middle. It does go around. But yeah, we have many different things. I think back when the Egyptians were around, and their pole star was actually called Thuban. And eventually down the road, I think Polaris will move away, and it will be a different star. It will be our pole star. And so there are many different things. I think there's even some constellations that were way back in the day. If you look like thousands of years ago when they did a lot of their star charts and stuff, we look now and those constellations aren't there. As well as they do change. Like, say, right now in the summer, I'm in the northern hemisphere. I can't see Orion. I can't see Orion at all in the night sky. And I won't be able to see Orion until closer to wintertime, at which then I will be able to see Orion's belt and stuff like that. And that's just down to the fact is that we're on one side of the sun, and so Orion is actually behind the sun. Like when the sun's out is when Orion's actually in the sky, but I can't see it. And when I come around, then Orion will be in my night sky again.
At the North Pole, Polaris always stays in the same place, and stars rotate around it. Strange if the universe is expanding.
As I said before, Polaris is actually moving, and you can look at you can look it up. The star chart showing from where Polaris was measured 50 years ago, even 100 years ago, and you can look at where Polaris is now, and there are star charts showing where Polaris has actually moved and changed orientation. And as I said before, back when the Egyptians actually, if you look at the records they kept, Polaris wasn't the pole star, it was actually Thuban at the time. We're talking about 3,000 years ago. So, yeah, Polaris does move. We see it. And as well as I said, if you watch Polaris in the night sky, if you do a time lapse, you see Polaris actually rotates around. It's not perfectly in the center above the pole. It goes around it by, I think it's about 1 degree. So it's half degree on one side, half degree on the other side, and the full from each side from this point to point furthest is about 1 degree.
NASA talks about planets in other galaxies, but we don't see a single space station in real footage.
What do you mean no, you don't see a single space station in real footage? People take video of like the ISS transiting across the moon, or even if they have a solar filter, transiting across the sun all the time. There's pictures, there's videos and stuff showing the ISS all the time. So I don't know what they're going on about this, but we see the ISS, which is like the International Space Station, all the time. This is done by amateur photographers. I'll put a video up of when I'll look one up. There's tons and tons out there. So here's right here where a fella used 2 different telescopes, 2 different cameras, and so you'll see that he got 2 different shots. So you'll see this the speed there, a regular speed, and then he slows it down a bit more, and then you can kind of see the second camera here, which is a bit more zoomed in, or a bit more magnification. Slow it down there again, and then he'll show a shot, final shot here. And there you go, that's the ISS. Now here's another one here. This is a big Dobsonian, so this is quite a big telescope, so you'll get a lot more magnification. They slow it down here to quarter speed. As you can see there, yeah, that's ISS going in front of the moon.
When building long railways, even over 13,000 kilometers, they don't account for any curvature.
What? I don't understand why anyone would think that the railroads don't account for the curvature of the Earth. To give you kind of a better estimate or calculation of the curvature of the Earth, the Earth curves 1 degree per 69 miles. Or you can say 1 degree is 60 nautical miles if you're on the ocean. You are laying track which can go over top of certain hills and certain terrain, which obviously you're going to encounter a lot more deflection of the track over, like going up or over top of a gradient of a hill or a different topography. So why would you think it couldn't account for the curvature of the Earth? Tracks are maybe maybe 50 yards at the greatest, or something along those lines. And so you're doing these segments, and obviously that metal is going to have some flexion up and down. So it does actually count for the curvature of the Earth. Laying railroad, especially when they're doing all their surveying and stuff like that, they do take the curvature of the Earth into account when laying these tracks. But the curvature of the Earth isn't something that is that drastic that is going to affect them. The bigger obstacles that they worry about is the terrain of like hills, mountains, valleys, stuff like that. And so that is what normally is a larger determining factor on laying track than the curvature of the Earth, because that is so gradual that that's not the problem. And as well as the gravitational pull of the Earth pulls everything to the center. And so according to the train, as long as it's got gravity pulling it down the center as well as over the curvature of the Earth, not a problem. But as I said, looking at the Field Railway Engineer's Manual, and we're looking here, you can see that the curvature of the Earth is taken into account when they're doing their surveying and stuff like that. So yes, 100% curvature of the Earth and all that is accounted for. So kind of there's a rundown here as well as citations. You can check it up for reference books and such. There you go.
If Earth were a globe, canals would curve and water would flow off somewhere. But canals like the Suez look flat and motionless. Gravity? Have you ever seen actual, direct proof of it?
I hear this from flat earthers all the time, and I find it's actually quite comical. So what flat earthers think is that if you see how the globe, that the gravity pulls everything down away from the globe. Like, if you had like a globe or see something like, they think if this is the globe, then gravity pulls everything down here to the bottom. But that's not the case. If you have like the globe here, everything pulls it to the middle. Down is towards the ground, up is away from the ground. So up is towards the sky, down is towards the earth, no matter where you are. So when they say that Suez, that canals and stuff don't work because water has to flow uphill, that's not the case, because that's all the same. Like, let's say this the Suez Canal, which is a sea level canal, but the Mediterranean and the Red Sea, there's actually about a foot difference between them, but there's no locks needed because it actually is cut the way that it connects the two bodies of water together. And so, and the water is just going to flow between them, and so there's no locks and stuff like that. All they've done is just took the land, cut into it, and connected two bodies of water together. That works perfectly fine on the globe, because the water is still being held to the globe no matter where you are all the way along that, because it's pulling it to the middle. Rivers flow from high altitude to low altitude. They don't care where they are on the globe. It's always high altitudes away from the center, and then as you go lower altitude, you go towards the center, towards the ground. So that's kind of stupid, and I think this is the fact that flat earthers always think that gravity should be like if you're holding a globe in your garden and you pour water on it. Why does water run off it? Well, because below that globe that you're holding in your garden is the planet, and the gravity is pulling everything down towards it. As for showing gravity, there's many experiments you can do or you can look up. One way is the Cavendish experiment, which you could actually make one at home and see the effects of gravitational pull of mass attracting mass.
Ask AI sometimes, it even gives flat earth info. Try it yourself.
Really? So they claim that if you ask AI, it'll give flat earth evidence. Okay, let's try it. Is there any evidence for the earth being flat?
There's no reliable evidence that the earth is flat. The idea of a flat earth goes against centuries of scientific observation and experimentation. Would you like to hear about some of the evidence?
Sure.
Okay, here's one way to think about it. Imagine you're on a ship sailing away from the shore. If the earth were flat, the ship would just get smaller and smaller until it was too tiny to see. But that's not what happens. Instead, the hull of the ship disappears first, and then the mast disappears last. That's because the earth is curved, so the hull dips below the horizon before the mast does. Want to hear another example?
Sure.
Okay, here's another one. Think about how time zones work. If the earth were flat, it would be daytime everywhere at the same time. But we know that's not true. When it's daytime in England, it's nighttime in Australia. That's because the earth is a sphere, and different parts of it face the sun at different times. Want to hear another example?
Is there any empirical evidence of the flat earth?
I haven't come across any empirical evidence that supports the idea of a flat earth. The evidence we have strongly points to the earth being a sphere.
Many proofs for the globe are questionable, like in Antarctica, where shadows shift in seconds.
I mean, has no flat earther ever been out of their mom's basement and walked to the sunny day in the park? Here, I'll show you an example. The exact same kind of phenomenon. Same thing you see with this with MC2s walking around in Antarctica. I'm going to show you a video of people walking around in Montreal, Canada. So unless you want to claim that's fake as well, you're going to have a big problem. Now remember the MC2 one, when he was walking around, the guy holding the camera was also moving and walking as well. But if you look at the people as they walk past here, you'll see the shadows flip from one side to the other. Pretty much almost at the same rate. Now this is a sunny day in Montreal. So unless you want to claim that somehow that these people aren't in Montreal and that this is somehow fake, which you're going to have to show evidence of that, then your whole conjectures over the fact of the shadows moving with in Antarctica with MC2, we was talking to Nathan Oakley, is just bullshit, and it's your misunderstanding of how shadows work, which is not unheard of, because flat earthers seem to struggle with basic things like how shadows and light work. But as you can see here, everything you claimed is shown quite easily. You step outside, touch some grass, look at the sun, and notice that everything you think is wrong.
Edited images of the globe. Pause and look, something feels off.
A lot of the images you see from the globe, like this one here, or of the Earth, are of composite images from low Earth orbit satellites. And as you go over, they take strips of images, and then they go along, take other strips and other strips. So sometimes what happens is clouds move. And so as the satellite has gone around the Earth and come back to take a picture again, those clouds have moved from one place to another. Now you can simply really easily see this. Take your phone, if you have one, for the new one, it doesn't have to be all that new, and do one called a panoramic shot, okay? Now what that's doing is it's a composite image, and it's taking loads of pictures as you pan around, and it's stitching them together. Now, if you happen to do that and you have, like, say, an animal there or people moving, you suddenly notice the people or the animal seems to double up, or there seems to be multiple of them, even though you go, hold on, there's only one. And that's because they're moving, and as it's taking those pictures as you're going along, it's taking a picture of the same thing several times, and it's stitching them together. And this is quite easily observed if you just simply get out and touch some grass and do something. But that's all they are. They're not fake images. They're called composites, which you take lots of pictures, put them together to make one big picture.
CGI is used in every globe Earth.
That's completely untrue. There's loads of real world pictures taken of the globe all the time. Examples you can look at right now is the Himari 8 or Himari 9. I think it's a new satellite up. Takes a picture of the globe every 10 minutes. You have the Goes East, Goes West from NOAA. They take a picture every about 10 minutes. Or you can look at something like the Epic satellite, which is in geostationary orbit, and you can actually watch and see the Earth rotation on that. And that takes a picture every several minutes as well. These are all physical pictures taken of the Earth all the time, not CGI. The one thing you'll notice is always CGI or drawings or cartoons is a flat Earth. You'll never ever once see an image of the fantasy flat Earth delusion that is a real picture. They're all drawings, cartoons, or sometimes even computer graphics that somebody has made on their own computer.
Video. Radio signals often reach far beyond the horizon past where they should be blocked by curvature.
That's actually not true. There's something called radio wave propagation, in which you can bounce or ricochet the radio waves off the ionosphere, and sometimes they work better at other times depending on atmospheric conditions and how many charged particles are in the ionosphere. Also, sometimes the radio waves are part of the EM spectrum, which is part of the light spectrum, and so they are subject to a bit of refraction from the Earth's atmosphere and the medium. But a lot of times they are easily just simply you get tropospheric scattering. You can get ionosphere radio bounce, many different ways, and that's how they can beat going over the curvature of the Earth. Sometimes is by depending on the frequency and the power, and obviously what you want to get across. It was and how much information. Then you can use different frequencies and stuff to bounce it off the ionosphere. Here's some examples of radio wave propagation off either the ionosphere or using just the curvature of the Earth. It's perfectly explained.
Time zones don't align well with a rotating globe. Neighboring regions with the same sun position often have very different local times, which fits better with a man-made system for a flat map.
So flat earthers don't obviously recognize the fact is that time zones are geopolitical, and sometimes are they will make up, say, a time zone for like a country, like China example, that they all wanted to be on the same time. Now, China itself, for everybody else, actually expands over about 5 different time zones, but China only recognizes that they're going to have one time over the whole entire country, and so that's why China has one time, but all the other countries around actually expand over 5 different time zones. Now, their example of showing like Afghanistan and China makes no sense, because Afghanistan is actually probably a few hundred, if not thousand, miles to the west of China. So I don't know why they brought that, because they're in a completely different time zone, because China's decided to make its own time zone, despite everybody else is around them. Because really, the clock and whatever time you want to say in your country, it's up to your government or whatever your people want to decide to say. And you don't have to conform to what everybody else has around you. And remember, time zones are only geopolitical. And sometimes there's some countries that they want to be part of the same time zone as another country for maybe trade or to have continuity between the countries. Like I said, China expands over other time zones of other countries, but they decided to have their own one for themselves. And Afghanistan and China aren't even close.
And finally, more and more people believe the Earth is flat. Why do you think that is? Because it's nonsense? Or because it's the only idea that makes sense? Look closer. The truth reveals itself.
And finally, there's more and more people leaving the flat Earth, realizing it's a stupid cult ideology that actually is not based on any facts, evidence, or empirical data. There's nothing that actually supports the flat Earth. There's no evidence. I've been asking for years, and yet not a single flat earther has ever provided any empirical evidence, data, or measurements to prove or show that the Earth is flat. Everything in this video I have debunked with facts, evidence, and logic without even a second thought. It's quite easy. The flat Earth is nothing but a fantasy, delusional ideology that a lot of times borders on being a cult belief. But that's about it. Thanks for watching. Don't forget to follow me for more videos. Subscribe to my channel if you're not subscribed yet. Click the like if you like these videos. Comment down below. And remember, people, Earth is different than globe. Space is real. But don't forget, stay curious. Thanks for watching. See you again.